Hello everyone, my name is Andrew Becker, and as you can see from my timestamp, it is July 4th, 2022. Happy Independence Day, everybody. And today I'm going to be talking about our second project for calculus, the Grand Canyon Skywalk. And we're going to be trying to find the center of mass for this section at the end right here, this kind of U-shaped part of the walkway that sits out over the canyon. It's designated R1, and we want to figure out what the center of mass of this is. So let's set it up. We're going to treat this as a lamina, 2D representation. The mass is going to be uniformly distributed. That means it's going to have a constant density. In this path, we know that it is bounded by an outer semicircle with a radius of 35 feet and an inner semicircle with a radius of 25 feet. We know that the area for this total surface is going to be the area of the outer semicircle minus the area of the inner semicircle. And we also know that because it's symmetrical about the y-axis here, that the x-coordinate for our center of mass is going to be 0. But that begs the question, what is the y-coordinate? And that's what we're going to try to find out. So we'll start by taking some representative rectangles here, just like we did when integrating to find the area under a curve. Right? Each of these rectangles is going to have a width, which we'll call dx, and a height, which we'll call y. And they're also each going to have their own center of mass located at half the distance of y. Right? So they're going to have an area equal to y times dx, and they're going to have a y value for their center of mass that is half of the y value of the rectangle. Now, what we can do is integrate this with respect to the area of those rectangles rather than their masses, because the density is constant throughout the surface. The area is going to be proportional to that. So what we're going to do is integrate that midpoint, that y value for the center of mass of each rectangle, times the area of that rectangle, and divide it all by the total area of what we're evaluating. And we're going to start with the outer semicircle here. So we're just trying to find the center of mass for a semicircle with a radius of 35. And when we plug in our values, here's our midpoint, our y value for the center of mass. And here is our area of each of the rectangles, and this is the area of the whole semicircle. This is 1/2 because it's a semicircle, radius of 35 squared, times pi. So, the first thing we can do is pull out the 1/2 from the numerator because it's a constant, which will then cancel with the 1/2 in the denominator. And we also know that because this is an even function, we can change our limits of integration. Instead of negative 35 to 35, we can go 0 to 35 and multiply the whole thing by 2. We also know from our equation of the circle, x squared plus y squared equals 35 squared. When we solve for y squared, we can plug that back into this equation and get 2 times the integral evaluated over 0 to 35 of 35 squared minus x squared dx, all of that over 35 squared pi. So when we integrate this, it's a fairly simple integration. 35 squared becomes 35 squared x, and negative x squared becomes negative x cubed over 3. When we plug in our values, the 0 doesn't particularly matter because all these expressions all contain an x. That means that they will be 0. So we'll just have to worry about the upper limit of 35. When we plug that in, we get 2 times 35 cubed minus 35 cubed over 3, all of that over 35 squared pi. 1 minus a third is going to be 2/3. And when we simplify this down even further, we get 4 times the radius over 3 pi, since these 35 squareds cancel. And they leave 135 up in the numerator. That's going to simplify all the way down to 140 over 3 pi, which is about 14.8545. right? So that is going to be the y value for the center of mass of a semicircle with a radius of 35 feet. We can repeat this whole process for the inner semicircle. We'll basically just swap our upper limit and our radius values for 25. It's exactly the same, just with that swap. And we eventually come to 100 over 3 pi. I'm just going to move myself out of the way here. And 100 over 3 pi is approximately 10.6103. And that is going to be the center, the y value for the center of mass of that inner semicircle. And the big question is, what exactly do we do next? So we'll take what we know. We know that the y value for the center of mass of our outer semicircle is 140 over 3 pi. And we know that that y value for the inner circle is 100 over 3 pi. So let's take a look at them, right? Here's the lower one, the y value, the center of mass for the inner circle. And here's the center of mass for the outer circle, right? We know that they're both on the x-axis because it's still symmetrical. And when we take the difference of these, that gives us 40 over 3 pi, which is just over 4, and would be right down here. And clearly that doesn't make sense as an answer, because if we subtract this area from the total area is this outer circle here, right? And if we subtract this inner piece, we would expect the center of mass to shift upwards, not downwards. So what we're going to do is take that difference, take the y value for the outer circle, subtract it from the y value of the inner circle, and we're going to add that back on to the y value of the outer circle. So let's do that. We got 140 over 3 pi minus 100 over 3 pi plus 140 over 3 pi. That comes out to 180 over 3 pi, which simplifies to 60 over pi, which is approximately 19.0986. And there is our y coordinate. So we know that the center of mass is approximately right here, located at 0 for the x and 60 over pi for the y, right? So we can actually attack this a different way as well. We don't need to use x and y coordinates because we're dealing with circles. We can actually use polar coordinates, changes in a variable angle. So let's take a look at that. Here's that same graphical depiction. And what we can do is take this midpoint arc between the inner and outer circles. That's going to have a radius of 30 feet. And we can treat this basically as a curved line. And we can cut it up into segments, right? Each segment is going to have some length, which we'll call dl, and it's also going to have its own center of mass. And just like we did when integrating the semicircles, the length here is going to be proportional to the mass, right? Like the length of that each individual segment divided by the total length of that arc is going to give us the same as if we actually did the calculations and applied the mass to it. So exactly how do we find dl? Well, it's going to involve the radius and some change in an angle. We're going to call this change in angle d theta, right? So we can say that dl equals the radius times d theta. We also want to know what the y value is. X value we don't really care about. We know that's going to be 0, but we do need to know the y values for these points. So the y value is going to be equivalent to this larger angle, theta, right? Because y is on the opposite side from that angle, we know we're going to be using the sine of theta. And then when we take the sine of theta times the radius, and we're going to have an expression for our y value. And what we can do is integrate that y value multiplied by dl and divide that by the total area, the total length of this arc, which will be the integration of dl. So when we set that up, we have the integral of y times dl over the integral of dl. When we plug in our expressions, we get the integral of r sine theta times r d theta over the integral of r d theta. Now let's put in our radius of 30, right? And we're going to use limits of 90 degrees here because each of these is going to be equivalent. We don't have to evaluate it over the full 180. We can just do 0 to pi over 2. And when we plug in our radius values, we can see immediately that the denominator and one of the numerators cancels. And when we integrate that, the integral of sine is the negative cosine. We don't really have to worry when we plug in our limits about the zeros in the denominator because anything minus 0 is just going to be itself. So the denominator is just going to be pi over 2. But when we plug in our values for the top, we get negative cosine of pi over 2 minus negative cosine, which makes it a plus, of 0. And all of that's going to be divided by pi over 2. The numerator is also going to have the radius times. When we evaluate this, the cosine of pi over 2 is 0, and the cosine of 0 is 1. So we're left with 30 times 1 divided by pi over 2, which simplifies to 60 over pi, exactly what we got using the vertical slice method. I want to thank you all for watching, and I hope you have a great night.